Let me get into it. Gauge symmetries and quantum field theory integration. Gauge symmetries and quantum field theory, or QFT, are the mathematical backbone of the standard model of particle physics. They describe how particles and forces behave at the quantum level. Now, the Millar Cosmological Model, or MCM, accepts these structures as valid, but it takes things a step further. It suggests there's actually a physical foundation beneath these abstract equations. That foundation is called the memory fabric, a cosmic medium made up of quantum disappearance events we call blips, and the phase coherence patterns they leave behind. So MCM doesn't throw QFT out the window. It builds on it. It suggests that these mathematical gauge symmetries and quantum fields actually emerge as real patterns within this memory-based fabric. And this opens up a bridge that connects the tiny quantum world to the massive structures of cosmology and gravity, all in one unified physical narrative. Let's back up to how quantum field theory developed. In the early 20th century, physics split into two big ideas: Einstein's general relativity and quantum mechanics. Relativity explained gravity as the bending of spacetime by mass and energy. Meanwhile, quantum mechanics introduced a weird, probabilistic world where particles like electrons and photons behave like both particles and waves. These two views revolutionized physics, but left a gap: how to connect the continuous bending of spacetime with the grainy, probabilistic nature of quantum stuff. Quantum mechanics alone couldn't fully describe how forces work. It needed something more. That's where QFT came in. It said the universe isn't really made up of tiny particles flying through empty space. Instead, it's filled with fields that stretch across the entire universe. Particles in this view are just little ripples or vibrations in these fields, like tiny waves on a pond. By the mid-1900s, quantum electrodynamics, or QED, became the first quantum field theory to actually work, matching experiments with crazy precision, down to 12 decimal places. This success led to the birth of the Standard Model, which uses QFT to describe all known particles and three of the four fundamental forces: electromagnetic, weak nuclear, and strong nuclear. But how does QFT keep things consistent across the universe? The answer lies in something called gauge symmetries. These symmetries make sure the laws of physics stay the same, no matter how you shift or rotate the mathematical descriptions locally in space and time. Thanks to Noether's theorem, these symmetries directly tie to conservation laws like electric charge, energy, and momentum. The Standard Model organizes these interactions into three key symmetries: U1, SU2, and S3. First up, U1. This symmetry governs electromagnetism, things like light, electricity, and magnetism. It describes how the phase of a particle's wave function can change locally without changing anything measurable. This symmetry brings in the photon, the particle that carries the electromagnetic force. Quantum electrodynamics, or QED, is based on U1 and is one of the most accurately tested theories in physics. Next, this symmetry covers the weak nuclear force, which handles radioactive decay and particle transformations. It involves something called isospin, and it requires the W and Z bosons as force carriers. SU also combines with U1 to form the electroweak theory, a major success of the Standard Model. And finally, SU3. This one describes the strong nuclear force, the force that holds quarks together to form protons and neutrons. Quarks carry something called color charge, red, green, or blue, not real colors, but mathematical labels. The strong force works through particles called gluons, which themselves carry color charge. This makes the force incredibly strong and uniquely self-interacting. It also leads to color confinement, which explains why we've never seen a free quark in isolation. All these symmetries work because the Lagrangian, the mathematical description of a system's energy and behavior, stays unchanged when you apply these local transformations. This mathematical rule leads to the existence of photons, W and Z bosons, and gluons as force carriers. But here's the thing. In the Standard Model, these symmetries are purely mathematical. They don't explain why they exist or what physical medium supports them. This is where MCM offers something new.